In this video, we're going to find a power series representation for a function that we're able to express as a sum of two functions using a partial fraction decomposition. So, we have the function f of x equals x plus 2 over 2x squared minus x minus 1. We're going to write it as a sum of a power series, but we'll do an intermediate step of writing it as a partial fractions, getting a partial fraction decomposition. So remember that for partial fraction decomposition, we need to factor our denominator so that we can see what the form of the partial fractions is going to be. So the denominator factors as 2x plus 1 times x minus 1. So we have our x plus 2 over 2x squared minus 1 has to be a over 2x plus 1 plus b over x minus 1, and we need to figure out what a and b are. Clear our fractions here. The numerator x plus 2 has to be a times x minus 1 plus b times 2x plus 1. This expression has to be, this equation has to be true no matter what we plug in for x. So I might as well pick some convenient values for x instead of setting up a system of equations. One convenient value for x is negative 1/2 because it'll make this term go away. If I plug in negative 1/2 for x, I get 3/2 on the left-hand side. And we get negative 3/2 a on the right-hand side, so a is negative 1. Another convenient value for x to plug in is 1. Plug in 1 on the right-hand side, this term goes away. So we'll get 3 equals 3b, or b is 1. So our partial fraction decomposition for the original function is negative 1 over 2x plus 1 plus 1 over x minus 1. Okay, so we want to get a power series representation for the sum of these two things. This one, the second one, looks familiar. I just need to factor out a negative 1 out of the denominator. We get 1 over 1 minus x. That's our geometric series. Okay, so that 1 over 1 minus x is the sum from 0 to infinity of x to the n. On the other one, we're going to rewrite the denominator as 1 minus something. To start that, we've got a negative in front, so we've got 1 minus, and then a negative 2x to keep everything equal. So our x here has been replaced with 2x in our 1 over 1 minus x formula, if you will. So we'll replace the x with negative 2x in the geometric series. And then now we've got two things and get like terms. In particular, we can factor out an x to the n. So we'll get negative 1 to the n, 2 to the n, plus 1 here, and factor a negative out in front. All right, so when we want to know the interval of convergence, we need to know when each power series converges, because remember, for a sum or difference of power series, they both need to converge in order for the sum to converge, or the difference to converge. So this first one will converge as long as negative 2x is less than 1, or x is less than 1/2. The second one is our geometric series, which converges if absolute value of x is less than 1. So if we look at when both of them converge, well, this is a smaller interval, so that's the one we'll use. The absolute value of x is less than 1/2. It's the intersection of those two intervals. It's just that the one interval is inside the other. So our interval of convergence then will be the interval from negative 1/2 to 1/2, and the open interval in that case.